Hey y'all, today we're going to be talking about motion. We've talked about motion before in terms of the derivative of position is velocity, the derivative of velocity is acceleration, as well as with the integration side with our car movement. If we integrate our speed, we would get position, so distance traveled, things like that. We've talked about average rate of change. We've talked about average value. So we've kind of been working with motion this whole time in calculus. Really mostly from the derivative side, just a little bit with integration. Today we're going to focus a lot more on the integral side, but you're going to kind of see how motion can switch in between derivatives and integrals, especially as we get into the AP exam. But today, focusing on integrals, we're going to kind of keep three key things in mind. So number one is that the integral of velocity, so the integral from a to b over some interval, would be equal to the position function, specifically the position at b minus this position at A, which would give us that change in position over that interval A to B. Okay, the other two things, they kind of go hand in hand together, but we want to keep in mind that there's a slight difference between what we call net distance and total distance. So net distance is, so if I'm driving my car and I've driven 40 miles forward, then I go and in reverse for 10 miles, then that 40 minus the 10, I would have had traveled 30 miles from my original position. That's my net distance. My total distance is whether I'm going forwards or backwards. I just want to know every time I traveled. So if I go 40 forwards and 10 backwards, I would have gone 50 miles in total distance. And the way that we distinguish between that is our net distance, we just take a normal integral, while our total distance, we take the absolute value of that function inside our integral, which is going to take any negative portions of the function, any negative area, and it's going to flip it up to the top and make it positive. Okay, so with that in mind, let's look at our very first example. We have the velocity of a particle that is moving along the x-axis given by the function v of t is equal to 3t squared plus 6. And this one's going to be a non-calculator question. So we want to find the position of the particle at t equals 2 if we know that at t equals 4, the position is 72. So the key piece is that initial condition. And we've worked with initial conditions before in calculus, but our initial condition kind of tells us where our particle is at. It gives us a starting point, something to go off of. So we always want to start when we're trying to find position with wherever we know the particle is at. So I know at time 4 my particle is at 72. Then from there, I'm going to add on that integral or that area under the curve from whatever time I'm at 72 to whatever time I'm trying to get to. So I'm trying to go from 4 to 2. So I'm going to add the integral from 4 to 2. And then my function, 3t squared plus 6 dt. Okay, now before I can move forward, there's something you probably noticed. Right now our integral is going backwards, so we have to use our integral property to change this to 72 minus the integral from 2 to 4 of 3t squared plus 6 dt. Okay, and that makes sense. If I'm starting at 72 and I'm trying to go backwards in time from 4 to 2, I probably want to take away any distance traveled that occurred from 2 to 4. So from here, I can just integrate and plug in. So integrating our function 3t squared plus 6, we would get 72 minus our new function would be t cubed plus 6t. And then we are still evaluating it from 2 to 4. So from here, I can just start to plug everything in. So this is equal to 72 minus 4 cubed plus 6 times 4. Minus 2 cubed plus 6 times 2. Simplifying out a little bit further, we get 72 minus 4 cubed is 64, plus 6 times 4 is 24, minus 2 cubed is 8, and 6 times 2 is 12, but times the negative is minus 12. So from here, we would get 72 minus 64 plus 24 is 88. Negative 8 minus 12 is negative 20, which gives us 72 minus 68, which would simplify out to 4. Now, I do want to always check whenever I'm working with motion, does my problem involve units? Looking back, we just have velocity of particle. We have time as 4, 72. So we don't have any units given to us. So we can just leave our answer as 4. We also want to make sure that we actually know what this answer is. And this is the position at 2. And in this case of these notes, they're using P. Remember, we have also used S to represent position. We've also used D to represent position. So velocity and acceleration is always V, and A, position sometimes gets a little bit more mixed around. Okay, so as a follow-up B, we want to know what the total distance the particle travels from 0 to 7 is. So total distance, looking back up at the top, total distance is the one where we do the absolute value because I want any negative displacement to be positive, and I'm just adding up all of the travel that's occurred. So for our setup on this one, we want the integral from 0 to 7. So I'm not concerned about 72. 72 is where I was at 4, but I don't need to add a position. Okay, I just want to know how much travel has occurred. So I don't need to add on the 72 this time. So the integral from 0 to 7 of the absolute value of 3t squared plus 6 dt. And this one is non-calculator, but all of our absolute values that we've evaluated before, they've been linear functions. This one is a quadratic function, which we really can't do our absolute value, kind of splitting up all that kind of stuff. Doesn't really help us in this case. We could draw it, but it would be a curve, so we couldn't find nice geometric area, anything like that. So typically this question would actually just ask us, if it was non-calculator, to write or to set up the integral, but not to actually solve. So we're just going to leave this one just like that. Moving on along, number 2. Okay, we're going to do the same thing again, but this time it's going to be a calculator question. So the velocity of a particle that is moving along the x-axis is given by the function v of t is equal to 0.5 e to the t times t minus 2 cubed. And the reason this is a calculator question is because I don't even know where to get started with integrating that function. You'd have to multiply a whole lot of things out. You might be able to do u substitution, but probably not. So we would have a bunch of issues if we tried to integrate this by hand. So we would use a calculator instead, but we still want to go through the process of setting it up and then typing everything into our calculator. So for part A, we want if the position of the particle at t is equal to 1.5 is 2.551, then what is the position when t is equal to 3.5? So once again, I want to know the position, so I need to consider that initial point they give us, which is 2.551 at 1.5. So starting at 2.551 plus I want the integral of the interval, so 1.5 to 3.5, because 2.551 is at 1.5. So the integral from 1.5 to 3.5. And then my function, so 0.5 e to the t times t minus 2 cubed, and then of course dt because we are integrating t. You can also, if you want to, instead write this as the integral from 1.5 to 3.5 of just v of t. Since you're typing in your calculator anyways, you can be a little lazy and you can just say v of t on the exam or on a test. It means the exact same thing. I can see clearly in the problem v of t represents that function, so either one would really be fine. Okay, but typing this in the calculator, once we type it all in, I'm going to give you a little bit of practice on that, so pause yourself here for a bit if you would like. And then typing it in, you should get 18.470, and we are going to round it off at 3 decimal places. 3 decimal places is AP standard. So anytime we get a calculator question, always round it to 3. In this case, it was 18.4701. So that 1 just rounded our 0 to 0. Okay. Part B, we want to know the total distance the particle travels. So remember, total distance from the last one we talked about, that is our absolute value to make all of our area positive area. And then we do not need to consider that starting point, 2.551, because I don't care where I'm at some point. I just want to know how much did my particle move. So this would be the integral from 1 to 5 of the absolute value of 0.5 e to the t times t minus 2 cubed dt. And once again, you could replace that with just v of t instead of writing out the whole function, either one would be fine. And then once again, we would type this in our calculator. So pause me now if you want to get some practice typing in your calculator. And then once you type it in, you should get 913.067. Once again, it's 0670, so rounding off to that 3 decimal places, and then we are all good to go. So those are really our motion from an actual equation. Let's kind of pivot a little bit and let's talk about motion from a graph. So below we have the graph of the velocity measured in feet per second of a particle moving along the x-axis. The position P of t of the particle at t is equal to 8 is 12. So that's that initial condition they're giving us. We want to use the graph of V of t to answer the questions that follow. And A, we want to know the position of the particle at 3. So they didn't give us a equation for V of t, they gave us a graph. So when we're finding integrals here, we're going to actually use our graph and we're going to find our area under the curve. They gave us a nice geometric graph with some lines, so we should be able to make nice, easy, simple shapes. So let's look at A. We want to go to the position at 3. We know the position at 8 is 12, so we're going to start with 12. And then we are going to add that integral from 8 to 3. And then we don't have a function for V of t, so we're just going to write V of t dt, because that is representing the graph that we're about to find the area under. Now we do need to fix this a bit. This needs to become 12 minus the integral from 3 to 8 of V of t dt, so that we are going in the correct direction. And then from there, we're just going to use our geometric shapes to work this one out. So from 3 to about 6, we have a nice trapezoid. And from 6 to 8, we have that triangle. So calculating both of these out, this would be 12, not 12 plus, 12 minus, because we fixed it. 12 minus, our trapezoid has a base of 1 and of 3 with a height of 5. So 5 times 1 plus 3 over 2. Plus our triangle has a base of 2 and a height of 2. So 1/2, 2, and negative 2, because that triangle's height is below the x-axis. And then from here, 12 minus 5 times 1 plus 3 is 5 times 4, which is 20. Divided by 2 is 10, so minus 10. And then 2 times negative 2 is negative 4, times 1/2 is negative 2, but times a negative is plus 2. So this is 12 minus 10, which is 2, plus 2 is 4. And in this question, we actually do have units. Feet per second is our velocity, so our position should be in feet. Now, one nice thing about motion questions, y'all, is that your answers should make sense. So thinking about this situation, we know at time 8 we're at 12. We just found at time 3 we were at 4. Looking at our graph, notice from 3 to 6, our graph has all of that positive area because of our positive velocities. That means from 3 to 6, our car is moving forward, our particle is moving forward in the positive direction. From 6 to 8, it does move backwards a little bit, but it's a very small amount of backwards. So does it make sense from 3 to 8 for us to go from 4 all the way to 12, considering there's all that positive area? Absolutely. So the good thing with motion questions is your answer should make sense. So if you got something that didn't make sense, like let's say you got, you accidentally didn't get the negative there and you added 10 and subtracted 2 and you got 20, it wouldn't make a lot of sense for us to go from 20 to 12 from 3 to 8. Because our graph just doesn't represent that. So it's a good way to kind of check your work a bit. Let's look at B. B is what is the acceleration when t is equal to 5. Okay, so acceleration, now we're going the other direction because we get acceleration from velocity by taking the derivative. And in this case, we could find the derivative from a graph by finding the actual slope. That's the graphical representation of the derivative. We have nice lines, so slope should be pretty easy to find. I want to find the acceleration at t is equal to 5. So my slope at t is equal to 5, it's a line, so I would just do rise over run. My rise seems to be negative 5, with my run from 4 to 6 being 2. So for our acceleration at 5, we should get rise over run negative 5 over positive 2. So negative 5/2 for our slope, and then we want it to be in acceleration units, which would be feet per second squared. So nice little throwback to some stuff we were doing back in derivatives. Okay, part C, we want to know what the net distance the particle travels from 0 to 10. So net distance, remember, is our normal integral. It is positive displacement, negative displacement. I want it all. I want to know where my particle ends up, how much it travels. So I do not want to take the absolute value. So in this case, this is just our normal integral from 0 to 10. I don't care about that 12. I don't care about where I was at some point. I just want to know how much was traveled. So 0 to 10 of v of t dt. And we, of course, do not need to do anything fancy here because we don't have any actual equations. We're just going to find our area from the graph. So our first shape is a trapezoid, a much larger one, with a base of 2 on top and a base of 6 on the bottom, still with a height of 5. So this would be 5 times 2 plus 6 over 2. And then the rest of our area from 6 to 10 is a triangle with a base of 4 and a height of negative 2. So 1/2, 4 times negative 2. Simplifying that out, 5 times 2 plus 6 is 5 times 8, which is 40. Divided by 2 is 20. 4 times negative 2 is negative 8 times 1/2 is negative 4, which would give us 16. And then, of course, we want the correct units, so 15 feet. Now, switching it up the other way for part D, we want to know what is the total distance our particle travels. So remember, total distance is the one where we want to take the absolute value. The good news is because we already did pretty much all the work in C, we're not going to have to do anything too fancy here. So still the integral from 0 to 10. This time we want the absolute value of v of t dt. Remember, it is important that we write these integrals because sometimes on these questions, they give you a point for just setting up the integrand. Okay, so from here, all I'm going to do is make any area we found in part C positive. So that makes negative 4 positive 4. So 20 plus 4 would instead give us 24 feet. And once again, the nice thing about motion, questions should always make sense. So I had some negative displacement last time. This time it's all positive. So it makes sense that my total distance should be greater than my net distance. My net distance of 16 feet makes a lot of sense considering how much more positive area there is than negative area. So all of our answers realistically are lining up as we look. So let's keep going. Let's do one last one. We've done equations. We've done graphs. Let's talk about a table. Okay, so this table above represents velocity in meters per second of a particle moving along the x-axis at selected values of time t in seconds. In part A, we just want to know what does the value of the integral from 0 to 18 of v of t dt represent? Well, v of t is our velocity, so any integral of the velocity is going to represent position. In this case, it is just the normal value of the integral of the velocity. So we're going to take any change in position, whether it's positive or negative, which means this would represent our net displacement of our particle moving along the x-axis. And then we do always want to check, because what does the value represent? We want to make sure we're honoring the question by checking for any units. In this case, our velocity is in meters per second. So we'd say that this would be the net displacement in meters, because we want to be specific to our problem. All right. Now, part A was pretty straightforward. We've probably done it before. Part B, C, D, and E are just Riemann sums. We've done those before, but Riemann sums, you know, it's area under the curve. It's an approximation of area under the curve, but it's still area under the curve. So it's going to show up a lot with these motion questions. So go ahead and pause me for a little bit. I want you to practice your Riemann sums by working through B, C, D, and E, and then I'll go over them here in just a moment. All right, y'all. So checking over your work just a little bit. Our left Riemann sum, remember we're multiplying, in this case, 6 subintervals. They say of equal length, but it also just happens to be the 6 indicated in the table, which is perfect and awesome. It is a left Riemann sum, so we take the distance, which is in this case t, of 3, and we multiply it by the leftmost point. So 3 times 2.3, 3 times 2.7, and so on. Okay, calculating it all out, tossing it into our calculator, we would get 33 meters. Right Riemann sum, same distance, but we're doing it the other way, 6 subintervals multiplying by the rightmost point. So 3 times 2.7, 3 times 2.0, 3 times 1.3, and so on. We get 32.4 meters. So looking at this table, it's both increasing and decreasing, and then it increases again. So that's kind of why our left and right are actually pretty close together instead of usually they're kind of wildly one side or the other, because this function's kind of doing both increasing and decreasing, just depending at different points. Then our midpoint sum of 3 subintervals, so our total distance of 18, 3 subintervals would give us 6 in distance. So every 3 spots, we're taking the middle, so we take the middle point. So 6 times 2.7, 6 times 1.3, and 6 times 1.7, which gets us 34.2 meters. And the reason why that one's so much larger is just because of kind of the arbitrary nature of a midpoint when we're just working off a table. You know, the points can kind of be all over the place, so it can really throw and drive the numbers really differently. Okay, and then last but not least, our trapezoidal sum. That one takes into account all of our numbers, base 1 plus base 2 times height, divided by 2. We end up repeating those heights as we go all the way across, and we get 32.7 meters, which is right perfectly in between our right Riemann sum and left Riemann sum, which is usually where it should fall, a nice average of the two. So hopefully that was kind of a nice little review for you. Moving on to the very last one, part F, we want to find the average acceleration of the particle from t is equal to 3 to t is equal to 9. Okay, so we have 2 average equations we've learned. We've learned average rate of change, f of b minus f of a over b minus a, and we've learned average value, 1 over b minus a times the integral from a to b. Okay, the difference between the two is we use average rate of change to find the average of the function we don't have. So if I have position and I want to find average velocity, I would use average rate of change. We use average value, our 1 over b minus a times the integral, to find the average of the function we do have. So if I have the velocity function and I want to find average velocity, then I use the average velocity equation. So in this case, we have velocity, that's the information given to us in the table, and we want to find acceleration. So we're going to use average rate of change to find that function that we don't have. We're moving up the motion table in the derivative direction. Okay, so average rate of change is f of b minus f of a over b minus a. So in this case, v of 9 minus v of 3 over 9 minus 3, which, pulling all the values from our table, v of 9 is 1.3, v of 3 is 2.7. So 1.3 minus 2.7 divided by 6. And typing that one into our calculator, we do get negative 2.33 repeating on forever, or sorry, 0.233 repeating on forever. So we're just going to round that. 3 rounds 3 to 3. And we're just going to keep it at 0.233 because 3 decimal places is our AP average. Okay, or sorry, our AP standard, not our AP average. Okay, and that is our average acceleration from 3 to 9. Okay, now the follow-up part of this question, for what value of t in the table is this average acceleration approximately equal to v prime of t? And we want to explain our reasoning. So v prime of t is representative of what? V prime of t is the acceleration, correct? So where would my average acceleration be approximately equal, so not exactly equal, but approximately equal to the actual acceleration in the table? Well, we found the average from 9 to 3. So realistically, it could kind of be equal to the acceleration anywhere on that interval 9 to 3, or sorry, 3 to 9. Makes a little bit more sense. But I would say it probably should fall somewhere in the 6. I don't really love this question, so you probably wouldn't see it on an AP exam or a test. But I would say time t equals 6, I think is what they're trying to get us to land on here. So t is equal to 6, and as our reasoning, I would say v prime of t is equal to our acceleration. So v prime of t equals a of t. And our acceleration that we found is a good approximation of roughly a of 6, okay, which since it's supposed to be an approximation of that interval, it would be a good approximation of the acceleration at about 6 because it's the average over the entire interval. And so that would really be my justification here. All right, y'all. Well, that is kind of motion in a nutshell. There are kind of some different ways that it does show up. But really, this kind of hits on the high notes. Like I said, you'll still use average value sometimes. You'll use instantaneous rate of change. As we get into higher level motion questions, you'll switch more, kind of like our graphing one, between derivatives and integrals. They'll kind of switch in the same question. But this should set you up for success. Go ahead and work on the motion stations, and you should be good to go.